Okay, so it's a pleasure for us to welcome today Mireia Nievas, who is a postdoctoral researcher from the IAC Institute in the Canary Islands. Mireia started her career here working in light contamination, light pollution, before from the astrophysics department, and applying also to the selection of the site for what is now the Cherenkov telescope array. A very effective work that helped to settle Tenerife as the chosen place. Sorry, to choose La Palma as the setting place, not Tenerife, sorry. After that, she did a thesis on very high energy astrophysics related to AGNs, to the experimental study of AGNs. She continued inside the MAGIC collaboration. She continued this work at the DESI Institute in Germany, working inside the Veritas collaboration, where she did also very good work on calibration to calibrate the experiment. And nowadays, she is postdoctoral researcher in AC. She continues to work in the MAGIC and LST collaboration, still mainly in AGNs. And it will be a pleasure to hear from her insights about how intricate AGNs can be. Okay, so Mireia, it's for you.
Yeah, so
thank you very much.
I'm not really an expert on radio-galaxies. I have been working a little bit on this topic and trying to solve one of the main questions that we have around AGN observations, which is where are particles accelerated, where is the emission that we see spanning over the electromagnetic spectrum being produced, etc. And radio-galaxies are one of the most interesting sources to access that information, as we will see. So you probably know what an AGN is. It's basically the nuclear part of an active galaxy, which is a galaxy that is emitting a good fraction of their radiation, but it's not coming from normal stellar processes, but it's coming from something else, no? From another structure. Here you have some very nice examples, like the Centaurus A, MX7, Cygnus A, and Macarian 509. And yeah, what is interesting about these sources is that despite we have known that they exist for a very long time, so the field started with the discovery of the first extragalactic sources in the beginning of the 20th century. Then in the mid-century, in the middle of the century, we started seeing that some of these galaxies had some nuclear part that was very bright and it was probably not compatible with normal stellar propagation. There was a massive improvement in our knowledge of these new kind of sources in the 60s, coming from the start of the radio astronomy, and also combining it with optical studies of these new targets. And then finally, in the last part of the century, of the 20th century, there was another revolution coming from the study across the entire electromagnetic spectrum. We started to see that this radiation was not only concentrated in the optical part and in the radio, but it was also reaching X-rays at even higher energies. No? There was also a lot of work around trying to model these sources, trying to understand the different observational properties that we see around them, and trying to make this puzzle make sense in terms of a few parameters, such as the orientation of these targets, because they are not spherical, symmetrical, and the intrinsic physical properties, no? Such as the luminosity, the accretion rates these sources have, etc. So, as I said, like these sources are not, as we will see, really symmetric, so they are not spherically symmetric. They have some structure, and that gives us an important geometrical let's say parameter. No? So depending on whether we look at the sources from one direction or another, we will see different observational properties. There are also other more important, or let's say physical differences that differentiate these targets, and they are they are mixed together. So, for instance, we have the black hole spin, the power, luminosity. These properties might be related, so yeah, they kind of differentiate different targets. No? This is the basic diagram of such targets. No? So we basically have a central core, which is a supermassive black hole. We have an accretion disk, which is a flow of material that is slowly falling to the central object. We might have structures such as some torus-like component with dust, then some gas clouds around the central object, which are emitting optical lines. You study the optical spectrum to see these lights, and depending on whether they are closer and they move very fast, the lines get broken. And if they are farther away, they might move slower, and the lines are typically narrower. And finally, in some sources, we have jets. So these sources developed some jets that introduce significant non-thermal radiation. No? And you can guess that if you when you have a torch and you point to someone, that person gets blind. The same happens here. So if you look directly through the jet, you see some important effects here. The light that is coming from here, from the jet, pointing to you, overshines the entire structure and even the whole galaxy. So orientation is very important here, but you also have other properties. Not all sources are emitting in radio. Some are radio loud, they emit in radio. Some are radio quiet. They don't have these jets, they don't emit radio, etc. And also, there are sources that are intrinsically less powerful and others that are more powerful. And you have all these different combinations that give us a lot of different type of observational areas. You have here some of the properties, depending on whether you observe radiation in the different bands, etc. So starting from the non-jet, this is basically the same schema as before, but only for these kind of sources. I said here that we don't have jets, so the structure is basically the supermassive black hole, the accretion disk, then this material, this dust, is surrounding the object, and it can obscure the radiation that is coming through. So if you observe these sources, all these clouds that were emitting very broken lines in optical, you won't see them. You only will see the radiation, these optical lines that are farther away, they are slower, these clouds, so the emission lines are narrower. And if you look through this axis, you won't see these obscurations, so you will see the broken lines. And you have the safer one on blazars. And then in jetted sources, you have an additional component, which is this jet. I don't know if it works.
It works, but
yeah.
It's very faint.
Okay. So you have this jet that is composed by some plasma of particles, typically electrons, but there might be also protons and other types. And basically it produces another component that if you particularly look through the jet, you will see this potent radiation that is coming from. When you observe them through off-axis, you have a radio-galaxies. They typically have a central part that is quite bright, and then some jet that you clearly see in all these cases, like for instance, this example. Here. Then intermediate, you have some known as misaligned blazars, so they have kind of intermediate properties between the radio-galaxies and the last type that we will see, which are the blazars. In these sources, you basically see the jet overshining the entire electromagnetic spectrum, with radiation coming from all the way from radio to the most energetic frequencies, so gamma rays. And in many cases, you don't even see the galaxy, and not even the structures that we were mentioning before, like the emission from the accretion disk, the gas torus, etc. So this is the main differences that we see when we study the electromagnetic spectrum covering the entire bands. So all the way from radio to gamma rays. When you have a radio bright source, you will basically see the different components. So the equation is the acid torus and all the possible additional components such as a corona around the black hole, etc. But when you have a jetted source, since you are observing the source through the jet, you will see this radiation highly Doppler boosted, so really intensified. And you will mainly see this component, that is mainly non-thermal radiation. Typically synchrotron radiation, here at low energies. And at high energies, you might have other components such as inverse quantum scattering, maybe proton synchrotron and other types of processes. So here, it doesn't work because it is a PDF course. But here, it was a gift that it was illustrating this effect, not when you get from Radio-galaxies kind of phase you finally, when everything is aligned, you finally see this bloom of light that is oversharing. So I said that the radiation, particularly in the sources that have jets, and particularly when this jet points towards you, can extend over the entire electromagnetic spectrum. In particular, they are very interesting for very high energies because they are one of the most abundant sources that we detect in the most energetic rays, in this very high energy band. So when we study the sky in gamma rays, this is what you see, for instance, with detectors such as Fermi Lab in space. You see these skies, you clearly see the Milky Way, but you see a lot of individual sources here. These are mostly AGNs, no? These are the most abundant sources that we observe outside the galaxy. This is probably the most important instrument working in this band. This band is around the AEV and DEV. So we are talking about frequencies of 10 to the 20 hertz of wavelengths that are super short. They are below 1 angstrom. Here's the energy range. And this instrument is very nice because it has a very wide field of view and it tracks the sky continuously. So it observes everything with a cadence of basically one full coverage of the sky every 3 hours. So it's very good to study variability of different sources if they are changing the brightness over time. And it's also very good to study very extended sources. In fact, we have detected triangles that are coming from the Milky Way, for instance, that kind of resemble the jets or the lobes of our radio-galaxies. But there is a problem with this kind of space detectors. Of course, you cannot launch absurdly large detectors to space because it's prohibitively expensive. So at some point, since you typically have a spectrum in these astronomical sources that falls very quickly, so the number of particles that you get per area per time falls really quickly. At some point, you basically don't have statistics. No? So you need something different. And the way you typically detect these highest energies is to go back to Earth and use the atmosphere as a detector. So we built finally this Cherenkov telescope. No? They are observing the sky. They are using a large portion of the sky, typically with areas of 10 to the 5 square meters, in order to capture these photos. These are examples of working Cherenkov telescopes around the world. So we have Malik and Elistine Palma, who have buried us in Tucson, Arizona, near Tucson, Arizona, and we have Hayes in Namibia. There is another type of detectors that are also providing a very nice view of the universe in this energy range, which are these extended arrays of detectors, like LASSO in China or HAWK in Mexico. But I will concentrate in the first type, in the Cherenkov telescope, which are pointed observatories, let's say. So this is the extragalactic gamma ray sky in the very high energy band, so above 1 dB or around 0.1 dB. Okay. And it's mainly composed by the sources that where you have the jet pointing to you. These are called blazars. No? And there is a very small number of sources that are off axis, so the jet is pointing somewhere else. These are the radio-galaxy population. Among blazars, the majority are called ELACs. These are sources that don't have particularly bright clouds that are emitting optical light. So basically, all the emission is non-thermal continuum, synchrotron propagation and inverse quantum scattering. And yeah, only a few sources have something else in the optical spectrum, and they're called flat spectrum radio waves. They have these broad lines. So they are here. And the radio galaxy population is also very small, and you can understand this because these sources, since the jet is tilted, so it's pointing somewhere else, you don't have this magnification of the light, this Doppler boosting, so it's harder to see them. You need sources that are very close to you in order to have significant emission that reaches Earth. No? But this is the number of sources, these are sources that we have detected so far in this range of energy. Lower energies, we detect that. So the question still stands: where are particles accelerated, and where is the gamma ray emission in particular produced? In order to access this, we can think of the different sources that we detect in gamma rays. The most numerous are blazars, so let's start with them. In principle, the most obvious idea that we might have to try to understand where the emission is produced is through direct emitting. No? The problem is that in gamma rays we don't have a very nice, very good resolution, spatial resolution. So we need to go to other wavelengths in which we have a better resolution. Radio is one of those, and we have indeed imaged some of these jets from blazars. But since these sources tend to be quite far away, and the jet is more or less pointing toward us, this imaging is complicated, no? And we don't have that much detail to use these sources. Here are some examples, a few more, and a few more. No? Another method is to try to see the physics that are going on there in order to produce the emission. And here we need to distinguish two cases. The first ones are ELACs. These are the majority of the sources that we detect in very high energy gamma rays. And in these sources, what we think that we have is basically a structure that is very poor in material. No? We have a central black hole, we have an equation that is relatively inefficient, and then we have some jet. But we think that the lasting force, if it exists, it's very dim, let's say. So that's going to produce a lot of light, and doesn't have a lot of material. So in principle, we have this basic structure, not that is naked, let's say. And to complicate even more the problem, when we study the variations of the brightness across the electromagnetic spectrum, we see that often these changes are correlated between bands. No? So if you get a flare, so let's say increase in activity in gamma rays, then usually X-rays also increase at the same time. So it's very hard to try to see different regions that might emit their radiation or not. And maybe the only constraints that you can make on where the emission is being produced is through causality. No? Because if you have a jet that has some opening angle, if you have a very big region that is producing radiation, since that radiation needs to be coherent because of the processes that happen there to emit the same way. If you have a very big region, it cannot be very close to the center. It needs to be farther away. And as a consequence, the variability timescales will be longer. So you will see less rapid variations in the flux. No? When you have flat spectrum equations, the situation is different, and we can get more information because you have additional structures here that also emit radiation. So if you have a region here that is emitting gamma rays, these gamma rays can interact with the photons here that are producing the other components, and through pair production, it will extinguish and introduce cutoffs in the spectrum. The spectrum will end at some energy. No? And in fact, for flat spectrum quasars, if you have this emitting region very close to the central object, so inside this Broadland region, or the cutoffs that you will see are in the GED band here. And if you observe this thing with a Cherenkov telescope that typically is sensitive to energies much larger, you won't see any radiation. If you detect the source, then that means that the emitting region needs to be farther away. So we have another constraint. Now, apart from the causality that we had before for ELACs, here we can introduce the fact that if we observe the source, we detect the source with a Cherenkov telescope, it cannot be very close to the central object. But that's pretty much what we have for these sources. So the other candidates that we have are radio-galaxies. Unfortunately, we have very few. So we need to see what we can do with them and how to extrapolate it to the entire aging population. Fortunately, radio-galaxies are very good candidates. So in principle, they are very close by. So if we match them, we will get a lot of details. And in fact, with M87, you have a very nice example of this. This source is you can resolve the extended emission and the jet here in many wavelengths. So here is an example in radio. You see different structures at different scales. So you have these giant lobes. Then you have some structures here, a cocoon, that if you zoom in, you finally see the jet. You can continue zooming in into the central part, and finally you reach this first image that we have of the event horizon, that was made very recently. But this jet can be resolved in other frequencies, not only in radio. In fact, we have an image of this jet in ultraviolet, invisible. Hubble Space Telescope, we have an amazing image with the individual features or individual, let's say, structures inside this jet. We also have it resolved for one of the first times with an X-ray telescope in Chandra. And finally, we have measures all the way to the highest energies with Fermi and the Cherenkov telescopes, actually the three of them. So just to make you understand of the size of this source, these giant lobes, so the largest features of this structure, of its radio structures, which are plotted here with these contours, they are comparable to the size, the resolution, let's say, of Cherenkov telescopes. So in principle, with Cherenkov telescopes, it's one of the first sources apart from Centaurus A that are extragalactic, and in which we can start to kind of eliminate possible emission from some regions in the lobes. No? This source has been studied very extensively also, the time evolution of the brightness in different wavelengths. And in fact, we have found some interesting correlations. No? So by imaging the different parts of the jet in different frequencies, we have arrived to some estimations of where the emission is produced. No? So you see here how the emission evolves with time at different energies. So for instance, for very high energy gamma rays, for high energy gamma rays with Fermilab, for X-rays with Chandra in two zones, so near the core and near a feature that it was observing the jet, HST1. You have also data in optical and in radio, for different parts of the jet. And as you can see, there is some increase in the activity seen in very high energy gamma rays that happen at some points, in 2005, 2008, 2010. And they correlate differently with the other bands. In fact, for 2005, for instance, you see that in the core, there is basically no activity, so there is nothing going on. But if you observe this feature, this HST1, which is some kind of shock in the jet, you observe that the brightness goes up incredibly, both in X-rays, but also in optical. No? The situation is different for other flares. In 2008, there was again some activity going on in very high energies, but you see that nothing is going on this HST1. But there is something happening in the core. No? So you see that even though you see increases like in blazars, many increases of activity in this AGN, the origins need to be different. No? And this is one of the first sources in which we have seen this clearly. There is again another good data set that is being analyzed right now, which was coincident with a campaign done with the instrument that got this first image of this event horizon. So let's see what we get from it. This is also a source where we could, one of the first sources that we could do this exercise of trying to separate extended emission in radio from what is happening in a very small region around the core. So you can basically, with all this resolution in radio, you can start to shrink down the integration area around your radio data and try to see really the emission is corresponding to what you see in other wavelengths. Here, here you have to compare it some integrations in a very small area of 7.3 gravitational radius, compared with the traditional huge integrations that are 10 to the 5th or so. And you see really that there is a change in gravity. So this is what you typically would estimate for a laser, for instance, which you don't have such a great resolution. And we continue doing these exercises of trying to find new flares, trying to find new activity changes, trying to even find changes in the spectrum that we get when the source is trained. And this is interesting because when we study the source in a high state, when it is emitting more radiation, we see that it behaves like typical relaxed. So it becomes harder in the spectrum, so it emits more. It emits more at higher energies compared to the lower state, relaxed state. This is a typical behavior of a VLAX. So this again supports the idea that orientation really plays a role, and these sources might be related to VLAX. We have other sources as well. For instance, in this 3C264, this is an MET7 twin. It shares many properties with MET7, but it has some differences. First, it is a much larger distance compared to MET7. The jet seems to be shorter, and it has less nodes, but also has one stationary node, like for instance HST1 in MET7. And the spectrum also is really different. So this is much more VLAC-like. So it has more emission towards the higher energies than MET7. Again, images from the jet. In this case, we can resolve it very clearly in the optical. Here's images with the host subtracted, so we only see the jet. Here in radio, you can also resolve it, but not that clearly, at least in X-rays. More of the sources that we have studied so far, AGC 1275, this is a very interesting source because the image is impressive, the physics are messy. Because you have two galaxies actually. You have a background galaxy, which is the AGN, the giant elliptical galaxy, and in front of it you have a spiral galaxy that is colliding with it. And so you have here an example where you can study not only the effects of the typical AGN activity, but also the effects it might have with the colliding galaxy, with the spiral galaxy that has a lot of star formation. It has developed two major flares that we have seen in very high energies, and they are quite similar in terms of duration, so they lasted months. One of them was already published and well studied, the other one we are still working on it. And what people think that is producing these flares in the past is that we might have a jet that is helical in shape. So it changes the orientation relative to us of the mission, and when it is more aligned to us, we have more Doppler boosting, the emission goes up, the emission that we see. This is what we think is producing those flares that we see. Around this area of NGC 1275, this is in the Perseus cluster, there are more galaxies, and in particular we have these two guys here. So you have NGC 1265, this is a very interesting radio galaxy with two jets that are heavily bent, so they are not aligned in one line, but they are really bent. This has been detected only in radio optical, but not in X-rays, as far as I know, and definitely not in gamma rays. And we have this IC310, which is another very interesting source. This is a head-failing source. So in these sources, we only see kind of one jet, but we are not sure if it is just one jet or they are two, but they are very bent. We see them aligned. So the one jet scenario had some problems because in this case, it's collimated to very long distances, to basically 40 kiloparsecs. And it has the same orientation when you go into the larger scales and in the smaller scales when you zoom in. And this is very strange for a source that is in a cluster, because you have a lot of magnetic pressure here that should introduce some bending. There are also other ideas to explain what we see, because we often see this jet, this object behaving like a blazar, so like if the jet was aligned toward us. So there have been some proposals in which you have this bending of the two jets, and actually close to the central part, the jet is aligned to the observer, so you see the blazar behavior, and farther away you see this bending of the two jets, and because of the orientation, you will see through them through this line, you see them collapsing into only one line. No. Well, in gamma rays, this source was recorded in terms of variability, so it reached changes of doubling the flux emitted in a matter of 5 minutes. This is amazing for a source at that distance. And in fact, when you make some calculations of the sizes that you need of the region to produce such a fast variability, you reach sizes that are comparable or even smaller than the typical gravitational radii. No? So in principle, the emission zone should be really small, and the magic collaboration, for instance, produced this picture taking the idea of the emission that we think is powering pulsars, in which you have some magnetospheric gap acceleration close to the central black hole. It is also, well, recently we have also discovered other interesting aspects of this blazar or radio galaxy, depending on how you consider it. It has extreme spectral variability. So apart from this hard state in which we detected this huge flare in gamma rays, it has a more soft state with a spectrum much softer. So it is really dropping in flux over energy. And the changes in the location of this peak, so typically this is the spectrum of an AGN, of a blazar, and the changes in the location of this peak in energy change with 5 orders of magnitude. So this is really huge. Just finally, the two sources that we have detected in the south. First, starting from Centaurus A, which is one of the nearest, if not the nearest AGN, at only below 4 megaparsec. This is not a particularly bright AGN, but it is so close to us that the sizes of these giant lobes span 8 degrees in the sky. So we can get really deep observations into what's going on here. No? In radio, it is a very complex source because apart from these giant lobes, we have other structures that are changing when you go deeper and deeper into the central part. No? So you have a very compact radio core. So the core is very bright in radio. You have some jet and counter jet that is very close to the central object, and another jet that stands more to the kiloparsec scale, but there's only one side. We only see one of the jets. And finally, you have the two lobes that look quite symmetrical. What is interesting about the source also is that it is the first source of this kind in which we have resolved the emission in very high energies from the lobes, from these extended structures. No, this hasn't been done before for other AGNs, as far as I know. And in this case, with the HEADS collaboration, this experiment in Namibia, so is that this behavior, this emission from the extended structure only shows up at the highest energies. And at lower energies, you see mainly the emission from the inner parts, no? From the central parts. And finally, we have this other source that was recently discovered It's similar in many ways to IC310, but since it is detected only at very low significance, we don't have that much details yet from this guidance. In fact, the viewing angle is not very well constrained, and it is even compatible with having laser-like source. So with this, I finish. I hope I have convinced you that the message that jets are messy, so they are not something that is tidy or then and linear, but they have events, they have features there that are accelerating particles, are emitting radiation in all the energy bands. And in fact, it is something that we can access best when we have images. And the quest for localizing the accelerating zones and the emission continues with this. For some sources, we are starting to see through the complex emission scenarios, but it's far from the result. So, I think that's it. Thank you very much.
Thank you very much, Mireia. Do you have questions from her about the analysis of the mission?
I have a question. Maybe it's a bit stupid, but would it be interesting or would it offer some data if we had any way to mask the blazars, to mask the ADR or the jet itself out and just get the information from the part that is in principle outshined by the jet?
Yes, but how do you do it? Through polarimetry or something like that? Perhaps?
I don't know. I mean, I don't know if I'm a bit ignorant. See this matter, but I don't know how collimated the jet is and whether this is outshining the rest of the galaxies because the jet itself deposits energy in the galaxy itself in such a way that masking it out is essentially impossible. But in case we were able to mask it out, for instance, I don't know, if we had an extremely nearby laser and we could use one of these Kuiper belt objects or cloud objects that we were so lucky that they would basically cross in between the source and the telescope. I mean, doing like computations. If you do with some nearby asteroids. I don't know if that would be feasible or not.
I guess there the problem you would have is sensitivity. So the emission that you expect from these outer regions, they are extended, like for instance in Centaurus. I don't think it is that right. So maybe you go to the larger cemeteries where you start to have some this happening process or something like that gives you more photos there in the highest energies. If you can get something, but I don't think the sensitivity would be enough.
Yeah, all the way standard.
Perhaps I don't know.
I think in optical, if you try to use another object for data, it's going to be bigger object. And if you know a laser is close, you just separate it out.
Well, but yeah, of course.
It doesn't say.
If it is large enough, you already have to see it.
No, in reality, what you see the diffraction pattern. Really, that you see the
You can construct it out.
maybe from the diffraction pattern. It is not mere shadowing, it is also diffraction.
But if it is large enough, you already see it. You have enough resolution to resolve the extended part. And if it is a place where it is so far away that you can't resolve the extended structure there.
For me, what surprises me of the talk is that many things that I thought were were very clear are not so clear. So first of all, jets are not really jets, but they are like those rivers. They can change the direction, they have a lot of structure.
Yeah.
Then your question of what is the emission coming from? The answer is coming from many places. The jet.
I mean, in M87 you have up to 7 knots there. Some are quite static, some are cheap. We see 264, the one that Veritas detected. Those observations were wrong because there were 2 knots that were colliding. There seemed to be some flare activity there. It was not super bright, but there was some increase there.
So you have the core, the knots, the collisions between the knots,
And then some maybe extended
the lobes.
radiation flow there. So it might come from different parts. And it might be energy dependent. So actually what we usually feed our data with simple power law might not be real because we might have breaks there because we start to see some maybe extended emission like in I would say where spectrum suddenly becomes harder. Whether this is significant or not, maybe it depends on the rotation. Maybe for blazars it is not so significant, but it must be there in many cases. So things are not that simple. And in many cases, we don't have that much data. In blazars, where we can not do imaging, we don't have an idea of what, in many cases, what we have in the jet or how the structure is.
So we observe a blazar, we see something. In 2 years, we see something different. We say it has changed, and maybe it has not changed.
And we still don't have the even the picture for that blazer. We don't have a clear idea of what's happening there.
Okay, do you have any questions?
I'm interested about another way that you mentioned that you could resolve those higher energies and not lower energies. I mean,
Yeah, so apparently when you go to lower energies here, where the spectrum is softer, apparently you cannot see this structure. And apparently the relation comes from the inner parts of from other regions. I don't have more than this. I mean, this is a nature paper that high school already published.
And the very high energy is not collimated, it's isotropic, because we see it perpendicular.
Exactly. And these are not even the jets, so these small jets that we were observing in radio, these are some radio structures that are used that maybe are similar to these lobes that we see in our own galaxy. So maybe it's a residual activity from an ancient past of this radio galaxy.
Thank you very much. Do you know, Armando, if we have any questions from the YouTube channel?
Because it's a YouTube. No, it's a YouTube, so.
Okay, so it doesn't seem to be the case, so thank you very much.